Welcome you all. Today we will start from here. We last time did a 3.3 quiz. Now we will move to next one, and we start discussing 3.4. That is families of continuous random variable. Now for families of continuous random variables, so we have a definition that is 3.5. First one is the uniform random variable. So for uniform random variable, x is a uniform random variable if the PDF of x is fx of x is equal to 1 divided by b minus a, and x is between a and b, 0 otherwise. There's a theorem 3.6. It says that if x is a uniform random variable, first one, the CDF of x is f of x is equal to 0 when x is less than or equal to a, and x minus a divided by between interval x is greater than a and less than or equal to b, and 1 when x is greater than b. So this is CDF, and the expected value of x in uniform random variable is b plus a divided by 2, and lastly is the variance, and variance of x is equal to b minus a whole square divided by 12. So this is for uniform random variable. Now we move to next one. Next family is definition 3.6 is exponential random variable. Now exponential random variable, the x is an exponential. Lambda random variable if the PDF of x is lambda times exponential minus lambda x is greater than or equal to 0 otherwise. So for lambda must be greater than 0. Okay. Now if we move to next one, next there's a theorem 3.8. It says if x is and exponential lambda random variable fx of x is equal to 1 minus exponential minus lambda x, and x is greater than or equal to 0 otherwise. B is that expected value of x 1 by lambda, and C is variance of x is 1 by lambda square. Now next we have a definition here is 3.7, and it is about Erlang random variable. So x is an Erlang random variable with n and lambda if the PDF of x is lambda power n and x power n minus 1, then exponential minus lambda x x is greater than or equal to 0 divided by n minus 1 factorial 0 otherwise. So this is only true when lambda is greater than 0. Now based on this there is a theorem 3.10 says that if x is an long and lambda random variable then expected value of x is 1 over n over lambda, and variance of this random variable is equal to n by lambda square. Now there's a quiz, and quiz is 3.4, and quiz says that we have a continuous random variable x as expected value is 3 and variance is 9. Find the PDF that is fx of x if number 1, if x has an exponential PDF. So so as you know that for exponential PDF, so for exponential PDF when x is an exponential lambda random variable, then expected value of x is equal to 1 over lambda. Okay, and variance of x equal to 1 over lambda square. Since expected value of x given us is 3 and variance of x equal to 9, this implies that lambda is equal to 1 by 3. And we know that now we will plug in the values for PDF for exponential. So 1 by 3 exponential minus lambda, so lambda is x by 3. So for x is greater than equal to 0 and 0 otherwise, right? So this is the first part. Now next part of the question is asking us to x has a uniform PDF. Now for uniform PDF, now as you know that x is a uniform, that is AB, random variable. So we know that expected value of x in that case becomes a plus b divided by 2, and variance of x becomes b minus a whole square divided by 12. Now from using these, this implies that since expected value of x given to us is 3 and variance of x given to us is 9, so this implies that 3 is equal to a plus b divided by 2 and 9 is equal to b minus a whole square divided by 2. So this implies that a is equal to 3 minus 3 under root 3 and b is equal to 3 plus 3 under root 3. So now PDF become 1 divided by 6 under root 3, 0 otherwise between a and b, that is 3 minus 3 under root 3 less than equal to x less than 3 plus 3 under root 3, 0 otherwise. So this is the PDF we can write. Now the most important topic of this chapter is 3.5, and this is the most important topic, and we use a lot in it has a lot of applications, and this is known as Gaussian random variable. Now Gaussian is actually bell-shaped curves appear in many applications of probability theory. So the probability model in these applications are members of families of Gaussian random variable. The probability models of these applications are members of the family of Gaussian random variable. They occur so frequently In practice, Gaussian random variable are sometimes referred to as normal random variable. So let's move to next one. So let's look at the definition of Gaussian random variable, that is 3.8. X is a Gaussian random variable, that is mu and sigma, if the PDF of X is, so PDF of X is given by 1 divided by under root 2 pi sigma square exponential minus x minus mu whole square divided by 2 sigma square, where the parameter mu can be any real number and parameter sigma is greater than 0. Okay, now theorem is 3.12. It says that if X is a Gaussian mu and sigma random variable, then expected value of X equal to mu, mu and variance of X is equal to sigma square. So look here, if I plot this one to give you some idea how this look like. So it is like this as a bell shape. Here mu is 2 and standard deviation is 1 by 2. Now if I make another curve, they are also a bell shape. For this mu is again 2, but sigma is, so variance is changed here. Now there's a theorem that explains some important. So theorem is 3.13. It says that if x is Gaussian with mu and sigma, so y is equal to ax plus b. So this will is also Gaussian. If we give Gaussian input and make a new variable, then the new variable is also Gaussian, but only difference is when it is x is multiplied by a. Due to this, it becomes a times mu plus b, because mean value is always linear, but variance is a times the same. Okay, because actually say variance is equal to sigma square, so that's why it is a times sigma. So this is standard deviation actually. Now this is mean value and standard deviation. So now we have a definition, and this is important definition, and this is 3.9. It is for standard normal random variable. Now what do you mean by standard? The standard normal random variable is represented by z is the Gaussian. Gaussian 0 1 random variable. So if mean is 0 and standard deviation, then we can say that this is standard random, and we normally represent with z. Okay, so means that the expected value of z is 0 and variance of z is 1. So this is known as standard normal random variable. Now definition 3.10, and it says that standard normal CDF is represented by phi of z is equal to 1 over under root 2 pi from minus infinity to z square minus u square divided by 2 du. So this is a standard CDF, standard CDF. Now there is a theorem 3.14. It says that if x is a Gaussian mu and epsilon, sorry, sigma random variable, the CDF of x, that is f x of x actually is equal to standard normal CDF with x minus mu divided by standard deviation. So the probability that x is in the interval a and b is probability of a is less than x and equal to b is equal to phi of b minus mu divided by standard deviation minus phi of a minus mu divided by standard deviation. So this is very important relation, because we use this a lot, and you have to understand this very, very carefully. Listen this, that we have Gaussian random variable which has mu as a expected value and standard deviation as a sigma. Okay, so when mu is 0 and standard deviation is 1 or variance is 1, in that case the random variable is known as standard normal random variable. Now if we know the standard normal CDF, so we can easily calculate CDF of a Gaussian random variable with any mu and sigma. Okay, now from here we can also calculate the probability within an interval. Now before this, so we know that there's a formula that z becomes x minus mu divided by sigma. So this is the relation that used to convert from Gaussian to standard normal value. Now because we already know the standard, why we want this? Because we already know the table where we know all the values of standard normal Gaussian for CDF. So note that Z is dimension less, so it represent x as a number of standard deviations relative to the expected value of x. So we have a table 3.1 presents phi of z for 0 z is less than 2.99. Okay, so people working with probability and statistics spend a lot of time referring to table like 3.1 to calculate. It seems strange to us that phi z isn't included in every scientific calculator. For many people it is far more useful than many of the functions included in ordinary scientific calculator. Now do an example and just understand the concept, how we can use this table and calculate the probability. Now suppose your score on a test is x equal to 46. Okay, now your score in a test is x equal to 46. A sample value of the Gaussian, that is 61 and 10 random variable. Now express your test score as a sample value of the standard normal random variable z. Now this is in the Gaussian. Now we have to represent in terms of standard normal random variable. Now how we do that? So to find probabilities of Gaussian random variable, we use phi in table 3.1. Note that this table contains entries only for z is greater than 0. For negative values z, we apply the following phi of z. Okay. So there is a theorem that says that 3.15, and it says that phi of minus z is equal to 1 minus phi of z. Why? Because the values we have is table 3.1 only gets z is greater than 0. Okay. So we can use this to use the table. Now example 3.16, we continue with the same one, and we say that if x is the Gaussian 61 and 10 random variable. So question is what is probability that x is less than equal to 46. Now if we apply theorem 3.14 and 3.15, so we can say that okay, probability of x is less than equal to 46 is equal to f(x) of 46. Okay, so this is the basic definition of CDF. So this is if we use the formula, that is z is equal to x minus mu divided by sigma. So if I put x is 46 minus mu is 61 divided by 10, so it becomes when I minus it becomes 1.5 minus 1.5. Okay. Now that's why we can't calculate, so we need this theorem. So for that reason it becomes phi of minus 1.5. Okay, so we did this thing, the same result we have in previous example, that is minus 1.5. So now we apply theorem 3.5. This is equal to 1 minus phi of 1.5. So you can easily look at the table. Phi of 1.4 is equal to 1 minus 0.933, and the probability becomes 0.067. So that's why this standard normal random variable is very important, that we have actually what you say table we can use to solve the problem. So this means that you are lowest 66.7% of the population of the test taken. Now let's do another example, and example is 3.17. so further we just learn how we do that. So if you have a Gaussian, again if x is actually a Gaussian with same 61 and 10. Okay. Now question is that what is probability that 51 is less than x is less than equal to 71. So this is the question. Now we apply the formula that is z is equal to x minus mu divided by sigma. So it becomes x minus 61 divided by 10. So from here when we put 51 and 71, so when we put 51 it becomes minus 1. So this implies that this is equal to probability of, when we put 51 here, it becomes minus 1 less than z and less than or equal to 1. So let me rub this equality here, is only less than. Now we know that then we can easily calculate it. It becomes phi of 1 minus phi of minus 1. Okay. So let me write on the next page. So we have probability of 51 is less than x is less than equal to 71. So when we apply the formula, that is probability of 51 minus 61 divided by 10 less than z less than equal to 71 minus 61 divided by 10. So it becomes probability of minus 1 is less than z is less than equal to 1, which is equal to phi of 1 minus phi of minus 1. Now again we apply the formula phi of 1 minus, so minus can be written as 1 minus phi of 1. So from here it becomes 2 phi of 1 minus 1. Now if we look at the values at table and subtracted from 1, it becomes 0.683 is the answer. So this is the way we can calculate the probability. Now another definition here is 3.11, and this definition says that the standard normal complementary CDF what this means? This means that complementary is that Q of Z. Okay. So because CDF we say that it is equal to probability when Z is less than equal. What about when Z is greater than small z? So it is known as complementary. So this is equal to 1 over under root 2 pi integration from z to infinity and exponential minus u square by 2 du, or it can be equal to 1 minus phi of z, because this is a complementary one. So we have a table in your book that is 3.2 that deal with phi of z. Sorry, complementary, that is phi of z. Okay. Now let's do a quiz. Quiz is 3.5, and this quiz says that x is the Gaussian and Gaussian with 0 1, so it is actually standard normal random variable, and y also Gaussian, with 0 2 random variable. Now question is, first one, sketch the PDF. Okay, now first one is sketch the PDFs of f of x and f of y on the same axis. So the idea is to know that what is the difference between these two. Now so if I want to plot it, so it becomes so let me plot here. So this is 0, assume this is -5 and this is 5, assume this is 0.4, this is your 0.2, and this is 0. Alright, so first one, it will start here and goes up to here. Okay, so this is for f(x of x). For second one, it has more spread, so it will start here with same mean value. So this is for f(y of y), because they both have mean value, but only standard deviation or disperse is different. Okay, so y has more spread than x. Now next question he is asking from us is question number 2, and he is asking what is probability that we have -1 less than x is less than equal to 1. Now we can use into standard form. So actually for standard form, this is p of -1 is less than x is less than equal to 1, so it becomes f(x of 1) minus f(x of -1). Okay, now from here, because this is already in standard form, so it becomes phi of 1 minus phi of -1, or in other words, it becomes 2 phi of 1 minus 1, and we put in the value, it becomes 6 8 2 6. Now let's go to third question. Third question is find the probability of -1 less than y is less than equal to 1. So in this case it becomes y of 1 minus f y of -1. Now we have to convert into standard form. How we do it? So it becomes phi of 1 minus mean value is 0, standard deviation is 2, minus phi -1 minus 0 divided by 2, so it becomes phi of 1 by 2 minus phi of -1 by 2. So it becomes 2 phi of 1 by 2 and -1. When you plug in the values, result becomes 0.383. Now what is the next part? So fourth part, what is probability that x is greater than 3.5. So for greater than 3.5, so again we can use this for x, so it becomes q of 3.5. So now we have to use table 3.2. When we use that, it becomes 232 into 10 raised by minus 4. Now question number 5, what is probability that capital Y is greater than 3.5? Now from here we cannot use directly q, we have to put q. You put 3.5 minus 0 divided by 2, so it becomes q of 1.75. Now when we look at table 3.2 where value is 1.75, for q it becomes because this is plus, and we normally this is the complement, this is equal to 1 minus phi of wait, I tell you what happened, because in table 3.2 you have values that is greater than 3, but this is less than 3. So what you have to do, you have to use the complement, that is phi of 1.75. so you have to use table 3.1. so when you plug in the values, you get the answer, that is 0.0401. This is the answer. So this is your quiz, that we will stop here, continue in next video. Thank you.